All right, folks, so we're going to go over quiz number 9 right now. Okay, let me go ahead and share. Okay, let me see. I need to move this one out the way. Okay, quiz number 9, quiz number 9. All right. Quiz number 9. Okay, so I'm going to enlarge this a little bit. Okay, so number 9. Okay, so an active low pass filter passes frequency within its pass band. Okay, so this is from the handout from the website. Okay, so it's passing in the pass band right here between the 3 dB or the cutoff frequency to up to 0 hertz. Okay, so that's why the answer is A as in apple for number 1. Okay, for number 2, the output voltage of a practical low-pass filter decreases as frequency increases. So the answer is B as in Bob for number 2. As you can see, as the frequency keep on increasing, your voltage is keep on decreasing. Okay, so the answer is B as in Bob for number 2. For number 3, the output voltage of a practical low-pass filter is decreases as the frequency increases. So that's the same thing as number 2 and number 3 are the same. Okay, any question on number 1 or 2? Okay, no question. Okay, next set. Okay, number 4. Okay, when the number of poles of a low pass filter, okay, when the number of poles of a low pass filter circuit is increased, the frequency response move closer to the ideal. Okay, so this is what low pass filter. Okay, so we're going to be, as the number of pole increases, as you can see, we can move it closer and closer. This is your ideal. That's straight down here. So the more pole that you put in, the closer that it is moving toward the ideal circuit. Okay, so the answer is A as in apple for number 4. Number 5, when the number of poles of low pass filter is increased, the roll-off increases. So the answer is 5. For 5 is C as in cat for number 5. Okay, as you can see right here. Okay, so you got 1 pole in minus 20 dB, 2 pole will be 40 dB, 3 pole will be minus 6 dB. Okay, so increases. Okay, so that's number 5. Number 6, the corner frequency of a low pass filter circuit is defined by its 3 dB point. So the answer is C as in cat for number 6. Right here, so right here, the 3 dB, the cutoff. Okay, so right here, FC, represent your cutoff. That is at your 3 dB point. All right, or 0.707. Okay, so the answer is C as in cat for number 6. And so any question number 4, 5, or 6? Okay, no question. All right. Number 7. Okay. How many poles does a first order high pass filter have? Okay. So number of poles. Okay, so right here. Okay. So the order and pole mean the same, that refer back in the same. So you got orders and so the vocabulary for orders and pole are the same thing, order. So for high pass filter would be here. Okay, so same thing. It's going to be just like I said, we're going to be increasing low pass filter. Same right here. Okay, 1 pole. Okay, let me go back to 7. Okay, so the answer is C as in cat for number 7. Number 8, when the number of poles of a high pass filter circuit is increased, the frequency response moves closer to the ideal. Okay, so the answer is 8. 8 would be B as in Bob. Okay, so that is similar to, let me see where the circuit would be. Okay, So 20 dB, moving closer and closer. Just like you did on the low pass filter, same thing with the high pass filter. Okay, so the answer is B as in Bob for number 8. Number 9, the output voltage of a high pass filter below the high frequency cutoff point decreases with frequency. Okay, the output voltage of a high pass filter. Okay, so we look at the voltage wise. Okay, so we're looking at here at the cutoff. As you can keep on going this way, the voltage it decreases. Okay.
Sam,
the voltage, yes.
can you show that question again?
On number 7, no 9.
So it say the output for the high pass
Below the high frequency cutoff point.
Okay, so it's
So you got-
decreasing. It's decreasing if we're going left, but then I was assuming it's going from left to right, so it increases with frequency. If
But
that,
they said below the high frequency cutoff point. So you got, okay, so this is the cutoff point. So you're gonna be going from this point here, go this way.
Okay, so if we're saying going that way, then it decreases as the frequency decreases. But then
Let's see. So decreases with frequency. The output voltage of a high pass filter. Okay.
yeah, decreases with
decreases with the frequency.
So that means
decrease with the
decrease, voltage decrease. But at the same time, if we look at C increase with frequency, because the way I read it is it increases with increased frequency.
But this
I think both answers are correct. I
how
read
you
it the same
interpret.
way.
Right. So yeah, it's below the cutoff frequency. So look at, so that means if it's below cutoff frequency, that means we're decreasing in the frequency.
No, it just means but I read it the same way as Michael did. If you start from from left going to right,
From 0 and up.
Yeah,
it just seems odd to read it the other way.
Right. But I understand what you're saying anyway. That's fine. No problem.
Okay. Yeah, just the wording here that it's been added onto in the parenthesis here. So we're looking anything that below the high cutoff frequency.
Yeah, even though it's below it, I think we need to clarify whether we're going up with frequency is increasing, or whether we're talking about frequency decreasing. So I think that's just a word thing. So as long as we understand what we mean, then that's fine.
Okay.
All right. Thank you.
So yeah, so this is the question here. It's a little bit ambiguous. So okay, yes, I see your point on the B and C. Okay, so that's number 9. Okay, so any other question?
Credit for that?
Excuse me?
So do you get credit for that since the wording is ambiguous?
It's okay.
That's up to Mr. Pham to give you, Mr.
Now,
Pham.
the thing is, what they already telling you, below the cutoff.
Yes, it's below the
Then the voltage have to be decreased.
Okay.
So the output voltage, the output voltage decreases with decreasing frequency on the high pass filter. Okay, so Mr. Pham said B is the answer for number 9.
All right, Michael, I tried.
Thank you. Okay, so the next set, so number 10. Okay, so high pass filter roll off rate is directly related to the number of filters, filter poles. So the answer is A as in apple, like we mentioned here. Okay, so this is high pass. So 1 pole, it's decreased by 920 dB, and 2 poles minus 40, 3 pole minus 60 dB. Okay. So increases, so it directly related the number of pole, the number of the roll-off rate dropped by that. Okay, so number 11. So A for as an apple for number 10. Number 11, the response of a band pass filter is characterized by its center frequency at minus 3 dB. Okay, that is similar to So minus the 3 dB, which is here, the cutoff. So from here, from this point on is the band pass band, okay. Okay, so at 3 dB, so the answer is D as in David for number 11. Number 12, a band pass filter generate maximum gain within its pass band. So D as in David for number 12. So within pass band, it started from here. So maximum, the more that you increase the frequency, the maximum would be hitting right here at the 0 dB. There would be no more gain, but that would be the maximum voltage output.
Now, Sam, on that one, we're looking at a band pass, not a high pass, right?
Yeah, band pass filter. Yeah, same thing with also same thing with band pass would be the
Right.
same thing. Yeah, at the 0 dB,
Mhm.
that would be your maximum output possible.
Okay, so looking at that chart, okay, you're saying, and no, the filter generate a maximum gain within its pass band, which is
Right. here.
between the two where it intersect the minus 3 dB.
Minus 3B, the lower cutoff and the upper cutoff frequency.
So this, oh, okay, I get it.
Okay.
Lower, okay. I interpret that as anything above minus 3 dB for C.
Right.
So, yeah, I got it. Okay.
And so anything within the pass band that will consider the maximum, or your signal will be very, very clear within this area. Okay.
Yeah, thank you.
You're welcome. Okay, so that's the answer is 12 for D as in David. Okay, any question on number 10, 11, or 12? Okay, no question. Okay, so a band pass filter's bandwidth and Q are they're indirectly proportional. Okay, so there's a formula right here. The quality Q equal F center over divided by the bandwidth. So therefore, if Q increases, bandwidth has to decrease. So, and that's why it's indirectly proportional. It's opposite of each other. So if you increase the bandwidth, you're going to decrease the Q. So the answer is A as in apple for number 13. 14, if you can find a bandpass filter center frequency with an oscilloscope by increasing the input frequency until the output voltage V out is at its maximum level. Okay, so C as in cat for number 14. Like I said, you keep on increasing your frequency, increasing, so that the maximum output, that is where you get the maximum output possible. That is your center frequency. And then if you keep on increasing and you keep on going, it will keep on decreasing the other way. So wherever the center is, that the maximum. Okay, so C as in cat for number 14.
On that one, Sam, just to be clear though, you do have to go to both of the 70% levels to be able to get the center. The maximum just tells you a range. It doesn't tell you a point. It's not going to tell you the center. Is that correct?
Well, you keep on increasing your frequency at the point at the center, you're going to have the maximum voltage. Say that this is like 10 volt, for example. At the maximum here, you're going to be getting like 10 volt. Here would be like less than here. It will be like 9.99 or 9.98 and or anything like that. So at the maximum.
Okay, so it does come to a point. Okay.
Yeah, it would come to a point. It would come to the maximum, and then if you keep on increasing, then it would keep on decreasing, going back down this way. And so therefore, at the maximum point, that would be your center frequency would be. And you will do that when you do some of your exercise on the op-amp application on the bandpass filter, and you will see it. Okay, you will get to do that.
Gotcha. Thank you.
Hey,
You're welcome.
Sam,
Yes, sir.
if you put that back up, yeah. The top of the curve here is flat, and I see why they're saying that. I think I pretty much agree with you. That point in the middle where you got your cursor at is 10 right on the nose.
Yeah, because you can't really make a good curve here, because then it's only increase a very minimal amount right here and right here until you're getting to a point it's maximum, and then after that it would decrease back a small amount at a time, but it's pretty close to the 10 range. That's why.
Right.
And your line here is really thick, so you can't really make it really apparent, you know.
Because the numbers are going to be the same, except one side is going to be low on the low side, and the other is going to be on the high side.
Yes, so anything here going to be the highest would be at the center frequency.
All right, that's cool.
Okay.
Thank you, Sam.
Maximum. Okay, you're welcome.
That normally, when you're working with op-amp application, okay, they're looking for the maximum voltage for the high pass filter. So you keep increase the frequency until they start going down. Then that is the maximum.
Mhm. And that's no matter if you're on the low side or the high side.
You have to be in the low side to increase
Yeah.
the frequency.
Yeah, so here would be the maximum, say 10 volt would be here. Now anything on this side would come to like 9.9 and 9.8, 9.7, 9.6, 9.5. And then after that, it's starting to getting down, keep on decreasing down this way. And this
I
side is
agree,
going
it'd
to
be
be
the same thing
decreasing.
on the other side as well.
Yeah, so keep on decreasing this side as well as decreasing on this side. But at the center, it would be the maximum.
Okay, gotcha.
Okay. All right, number 15, a band pass filter has frequency response characteristic of both a low and a high pass filter. So it's something like this here. So you got 1 point that is going to go here on the one side, and then the other side will at the low pass. So combine the two together, you got the band pass filter. Okay. So the answer is C as in cat for number 15. Okay, any question? 13, 14, or 15? Okay. So, and this one, we didn't totally cover on about the integrator and differentiators too much. I don't remember Mr. Pham covering this closely. So this one is a toss-up question number 16, 17, and 18. So an op-amp can be used in, now this one he did go over, he sort of touch a little bit on differentiator and the low and the high pass filters and the band pass filter. So the number 16, the answer is D as all the above. Number 17, 17 in active integrators, you have to use it has to have a capacitive feedback set in there, okay? Because you want to charge discharge.
Yeah, they can look into the integrators circuitry, and they can see the capacitor will be a feedback capacitor. However, differentiator, then they will be resistor feedback.
So you need a
Not only
resistor.
the different.
Right. So the answer 17 is C and number 18 is B.
They're
Okay.
just asking for recognize. Is it an integrator or differentiator?
Okay. So that's how you distinguish the two. So if you see a capacitor, it's an integrator. If you have a resistor, you have it's a differentiator. Okay. All right. Any other question? Let me see. Okay, look like everything's good. Okay, back to you, Mr. Pham. Thank you.
Okay, thank you, Sam.
You're welcome.
Okay, so welcome. Hello, everyone. Make sure you understand next Monday, January 17, that holiday. Okay. And the next week, we'll start a register for your guide for the spring 2022. You understand in the past, someone asking me, how come your guy cannot get the certification to complete the program? You understand that to complete the program, you need two different things you must be done. Lecture and the lab. And it is not really good for us. They closed the lab from 2020 up until the fall 2021. They allow certain people to get into the lab. That's why. Okay. That's too long, 2 years. I couldn't believe it. Normally, I want you to get a certificate so that can help you to do whatever you want. But we're working under the San Diego City. We have to follow their rules. I completely myself out of control. They control everything. I thought this the fall 2021, I can go back to normal, but it not happened. That's just a part of it, okay? So for the spring 2022, okay, I try to evaluate to see who done for left vote, who done for the lab in the textual. Then you can get the completion certificate. Who not done for the D lab, that means you have to be on textual. Then will be end of textual, you will be get the certificate. We try the best in order to help you to do the D lab. It's not like left vote. D lab, you can build a circuit at home. Develop your software to test the circuit at home. Only thing is you have to need the instructor verify your circuitry working. Okay, so not much time you have to stay in the lab. The lab phone, you must be in the lab. The thing is, you cannot do anything without the lab phone setup. Okay, so do you get any question to me?
I have a question, Mr. Pham. Just wondering about, so what does it all mean for those of us that are in electronics 1? Do we move on to electronics 2? Is that what we sign up for, or is that still under evaluation?
Now the thing is, if you be in the tech 1, okay, and you already done most of things except for the lab. The lab phone is not done. It's not your problem. Okay, it's not your fault. It's not mine either. The thing is they close. So you still moving to tech 2. However, you have to do 2 things. You have to do lab vote, and also you have to do the lab. That's it. That means you're working a little harder in the spring 2022 in order to get a completion.
Okay, and then the second question I had, there was an orientation tonight. I skipped it because I did it before. I'm wondering though, do we get a reference number to be able to sign up next week?
Next week we'll give you the access code. Okay. For the student in the program, next week, I think on Tuesday, we'll given you the access code so you can register for.
Great, thank you.
Either take one or take two. The thing is right now, cities still get a problem up until January 18. They're not working, like in the fall. They're working just 1 or 2 days or 3 days. And the other part, they will be online. I don't understand, but what can I do? But I try the best to helping you to get the lab done, especially for digital lab. Okay, anything else?
Hey, Mr. Pham, are you saying that the administrative offices, they won't be open until January 18th?
No, they're not. They start supposed to be until January 18th.
But you don't know for sure. That's what they told you, but you don't know for sure.
Right, after January 18th, see what happened. They not tell me.
Oh, okay, I get it, I get it.
I don't know. You can try to understand that. However, what I recommend to you, okay, try to really understand what we already done, semester to semester. Anything we're talking basically DC, you have to understand electronic, bipolar, amplify, op-amp, whatever. Filter, JFET, try to really understand. That will be helping you a lot. The thing is, you understand everything, different semester, I have to try to update the way we teaching, hopefully can help you to understand. Okay, so today we will start with the JFET. We already done some. Let me share my screen.
Mr. Pham. Question?
Yeah,
Will you have extra 4550s?
what do you mean 4550?
I need 2 more 4550s burned. Is that possible?
You're talking about the IC or what?
Yes, please.
Oh, timer, right? 555, right?
Just a 4550.
What type of the IC?
Microcontroller.
Oh.
Did you change?
You're talking about the microcontroller of the system test.
Yes.
I need to look at it.
If you have extras, I need 2 extra, please.
Okay. Okay. I will look into it.
Thank you.
Now, after 2 years, I forgot everything. Okay. So we try to finish that thing today. We already talking about JFET amplifier. The first one we want to talk that a common source amplifier. Okay. So what I expect you when you're looking into the amplifier circuitry, you're able to telling me what configuration for this amplifier. They get a common source, common drain, and common gate. Okay, that's not hard to do. Only thing must make sure common source amplifier. Okay, then input applied to the gate, output applied from output coming out from the drain. That is the first thing you must know. The second thing is the input and the output will be out of phase. You can see that opposite. Input positive, output negative, and so on. That is the second thing. The next thing, they can ask you what the bias circuitry they're using to build this amplifier. And you understand the bias, you can get the fixed bias, cell bias, and voltage divider bias. Okay? Then you must know which one. For example, for this circuitry, when I'm looking into that, I know they're using cell bias. Why is cell bias?
Because there's no battery at the gate.
Yeah, exactly. So there's no negative voltage applied to the N channel right here. That is the cell bias. And before you want to do anything with the amplifier, then you still have to calculate the VGS, ID, or whatever. And you understand the cell bias, you need the graphic. Okay? However, we don't deal with the graphic. So that's why they must given to you a little more information. For example, here, they say, I given you 1 volt, VS 1 volt. Then you can do the rest for the calculation for the bias without the graphic. That means you can calculate the ID easy.
5 milliamps.
Yeah, this is the current IS. IS ID again must be the same. So you take the VS divide RS, you get the IS. That means you get the ID. And after that, you can calculate the VGS ID, okay, and VD, whatever you need to do calculation. That for DC bias. And on this circuitry here, another thing, I'm not going to detail yet, but the general thing you must know. Capacitor here, C in, C out, that will be AC coupling or DC blocking. Okay? And the capacitor here, they will be a bypass capacitor. And the question is, bypass what? That will be telling you for the AC, the current not go through RS, they go through the capacitor to the ground. So that will be bypass RS. That's the minimum thing. You're able to let the people know. Normally, they're not asking more any calculation. They're asking for general understanding. Okay? And now, if whoever you want to go a little more in the detail, you go to university, that's what you need to do. That means they're talking about AC. Okay? module for the common source. So they already telling you in the dark here that the JFET inside. And only thing that you can see, they can get the R small d. Basically, that output resistance inside the JFET. Normally, they ignore that one. Okay? The thing is too big compared to the output resistance here. So, in here, they can asking you for input impedance. That means you input right here, you're looking into the amplifier. You get GI. That's what input impedance. And they equal RG. Okay? And output impedance. That means from the output you're looking into the amplifier. You can see basically you get that one in parallel. However, they ignore R small d. So they will be equal big D only. Okay, that means that one, drain resistance. If you get a load, then you can get another resistance here. And also they given you the formula. If you want to calculate the voltage gain, then they will be equal minus GM times RD. Minus sign only telling you input, output will be opposite. Okay? And also here, phase relation. They already telling you common source amplified configuration has 180 degrees phase shift between input output. That's what I want. Make sure you're able to get your information. It's a very, very basic general. We not go too much in the calculation. If on the test you get the calculation, I given you the formula. Make sure you know how to do calculating. Okay. Another one, that one here. Okay, let's see. Now, next one, common drain. Common drain, they get another name. Source follower. How come they call a source follower? When you read a source follower, do you understand why? Why they say a source follower? Who can telling me? Why they get the name source follower?
V out something.
Okay.
With
Now,
the common drain, the output is taken from the source and the drain does not have a resistor.
now that is telling you to recognize this is a common drain.
Right. And
However,
the output is taken from the source.
right. However, what I asking you, how come they come up with the name source follower?
The output is identical to the input. It's
Exactly.
following the input.
Exactly. The thing is that the output and the voltage at the source identical, same, right? So that's why they get another name is source follower. That means V out will be following whatever voltage at the source. Okay,
Is that from the AC point of view, right?
that we're talking about AC.
Right, okay. Because then the capacitor passes AC, not DC.
Exactly. That's just DC blocking.
Right.
Okay, and now in order to recognize common drain, input applied to the gate. However, output will be coming out from the source. Okay. I said, whatever we already talked to you, I already tried to display, and you must be spend the time to read it, think it. Okay. So when I'm looking circuitry, I know that common drain or source amplifier. And input impedance, you look in this way. Output impedance, look into the amplifier. Okay. And also for this circuitry, they're using what? They're using cell bias to build common drain amplifier. That is at least, I say at least you must know. And this just the AC drawing, okay? We don't care too much thing. G in equal the same RG like the other one. G out, they will be equal RS parallel with our 1 over GM. And the gain will be GM times RS divided to 1 plus GM times RS. That is what you need, the formula, okay? And also the input output will be in phase. Okay, common drain amplifier.
Mr. Pham, one question.
Yeah,
If you go back to that, please. Yeah, right there. You have two different formulas. You got an AV on the left and an AV on the right, and the formulas are different.
you understand on this formula, they also calculate the R small d right here inside the JFET. And we already said we ignore that resistor.
Okay, so that formula there that you crossed out, we don't use that one.
Right.
Okay, thank you.
However, if they wanted RD, then you calculate again by this formula. Okay? But normally, you will be calculated again by the formula here.
Thank you.
You're welcome. I said when you're doing the lab and you're doing the test or the quiz, if you need the formula I given to you, we not expect you can memorize those, okay? No, you know how that circuitry working, okay? The detailed calculation. If you go up higher level, then you're able to get more. Let's see. You see on that one, they say I out. Where is the I out? You understand that you get a current here. That will be GM times VGS. That's what right here. Okay. My question is, where is V out? You can see right here, right? I out. So the I out will be go this way. Basically, they will be opposite. So that's why they given you the calculation here. IIS, that means they go this way here. Minus GM times VGS, that means this current. And then also they can get I out equal V out divided to RS. If you get the V out, you divide to RS, that's telling you get the IRS. Okay. And also they can tell you VGS, that means voltage, okay, from here to here, okay, VGS, and the V out, that will be the same voltage, okay, but they differ. So that's why they say I out VGS and minus V out equal minus V out. And they keep going to substitute to calculation. Okay. So they come up with G out equal RS parallel 1 over GM. Okay, that's what they try to do that for you. Let's see. G out right here. But that you must detail, okay? And you see you get two formula. And this second one, they using R small d, internal output resistance of the JFET, and we're not supposed to use. We're using only the first one.
And the same thing with the gain
Right,
above. The bottom formula where it has the gain at.
right, same thing.
You X that one out as well, right? Yeah, there you go.
Okay, now, if they given you that one, common drain, they given you VGS Q 2.86 volt. And also they given you IDQ 4.56 milliamp. You think you can do that one, right? Calculate GM0, calculate GM. They want to get the G input impedance, output impedance, and the gain. Okay, so
like sometimes he might not talk like that. It's like he's not fast. He's like that. He's like that. That's his love language. that okay, listen. You're way more into like the party bar
Can you
scene.
mute the mics, please?
And
Okay, 30
you
minutes.
want doing, going out, going like walking around.
Okay, what I want you to do, go ahead and try to calculate A, B, C, D, E quickly for me. Just a few minutes. Whoever get answer, let me know. You know the formula GM0. Is it the 2 times I DSS, right? Divide VGS off. Okay, so on this one here, they supposed to be VGS off, not repeat. We're not going detailed, so we don't care that one. So basically that will be equal to times IDSS divide VGS of absolute value. GM equal GM0
Mhm.
times 1 minus VGS over VGS of.
GM0 was 8 milli.
Okay, so you get 8 millisiemens, right?
Right.
So what happened to GM0?
That's
Yeah.
GM0. GM0 is 8 millisiemens.
Okay, GM. And also, let's see, GE. RG. GL. RS parallel 1 over GM. Okay, and AV AVGM times RS. Divide 1 plus GMRS. That's only thing you need to calculate it. And I already get the formula for you. Who get the GM?
GM is 23.5 millisiemens.
23.5.
ZN is 1 meg.
Exactly. In order to calculate the GL, first thing you have to calculate 1 over GM. Then that will be parallel with our X.
Mr. Pham, for
Yes, sir.
G, I got 5.72
On what?
GM.
Okay, you get a different answer, right? Okay, so now we try. GM 0, 8 milli. Okay,
Mhm.
1 minus VGS is minus 4, right?
No, you got
VGS
2.86. Up top, you got VGSQ equal 2.86 volts. In the black, up top.
16 or 1.6, 60.
No, it says a DC analysis of the source follower will result in a VGSQ equal 2.86 volts.
VGS 2.86.
Right.
Okay, then now VGS here.
VGS off is negative
Yeah.
4 volts.
Okay, so they will be equal 8, right? Times 1 minus 2.86, right?
Right, divided by negative 4. 2.86 is not negative. There's no negative in front of the 2.
Okay, let's see. Divide to what? VGS of minus 4, right?
Right, but the 2.86,
Yeah,
there's
I
no
understand what you're talking about. Right here, right?
right, there's no negative, it's positive.
Okay, I think they got the wrong one.
So you want it to be negative?
Yeah, that's the N channel.
Okay. All right, then my
Minus-
answer, my previous answer would be wrong because I used it without the negative.
Mine's wrong too, it seems. Should be 2.28.
Okay, so you 2.28.
Anybody got the same answer?
Hold on. Square this times 8.
2.28. That's the correct answer.
Okay, now for GM, now doing it the other way, I get 0.00064. which is the same as 0.64 or 0.65 milli. That's for GM.
The other student get 2.28.
2.28.
Okay, now see 2.86 divide 4. Okay. Minus 1. Okay. Time number 8. 2.28. With the speed, take your answer.
Okay. Okay, so minus is a plus. So plus the plus. And then that's squared.
Not square.
Oh, there's no square on there?
No.
Oh, that's why I messed up. Yeah, GMO, that's only when you're doing IDSS.
Okay.
Yeah, you, okay. 6 divided by 4 equal that. And then minus plus 1 equal, and then times 8e. Okay, yeah, it's 2.28 millisiemens.
Okay, now my question is, if I given to you that calculation for GM, take you how long? 1 minute or 1.5? Or 2 minutes? The thing is that is the one I given now in the test.
Now, I had put a square on that parentheses.
Yeah, I know you're wrong. But I try to say, take you how long to get calculate the GM when you already get everything.
You can do it fast. It's just that, like I said, I had the square on there.
But you think 1 minute, okay? Or 1.5 minutes?
Everybody's different, so maybe like, I don't know, 1.5, 2 minutes.
1 minute should be fine.
Okay, the thing is when I try to given on the test, I can given you 2 question calculation for 3 minutes instead 3 questions. Okay.
Michael's got a better estimate than I have. He says 1 minute should be fine.
Okay, so G out. Tell me who get G out. The thing is I need the right answer for the student. They cannot following. They can review later. Okay, RS that means 2.2K. Okay, and parallel with the 1 over GM. So you need to know what our 1 over GM. 1 divide 2.28. Milli, that means 10 power minus 3. Okay, 1 over 1 divide 2.28. You get 0.38. Four, 3, 9. Time 10 power 3. Okay, so basically 1 over EM equal 0.439 KO. Okay. And RS will be parallel with this one. So GL will be equal 2.2 times 0.439 divide 2.2 plus 0.439 equal
0.366.
0.366 KO. Okay. The last one, whoever get IAV, let me
Hey,
know.
Mr. Pham,
Yeah,
well, I was gonna ask you, like, when you do 1 over GM, you got the 1 on the top and the GM in the bottom is 2.28 millisiemens, right?
yeah, that means 10 minus
Okay,
3.
I know, but let me finish. Okay, so then if you take the reciprocal of that, wouldn't that be 438.6?
Yes, and which is equal to 0.439 kilo ohm.
Okay,
The thing is you're using IS in kilo, so they
Yeah,
have to be the same.
okay. I
these
see what
two,
you're
yeah.
saying. Got you. So Z out is basically what, 366?
0.366 kilo.
Yeah, but I'm saying if you could say 366.
Exactly. Oh,
Yeah, ohms.
yeah, that's converting.
Yeah. No, I was just checking my answer. Thank you,
Okay.
Mr. Pham, and thank you, Michael.
Okay, who get the gain? Just let me know the answer.
0.494.
0.494.
Yes, 494.
Okay, so who else get the same answer? So the answer will be correct.
Hey, Mr. Pham, my question on this one here, that's a small gain. So based on your experience, is that about what the gain should be?
Yeah, they have a no gain. Not much. You understand the JFET only they get a benefit for high input impedance,
Right,
not the gate.
not the gain. So we should be getting a number like under 1.
Normally,
Okay.
okay?
All right.
So we can do this one. They just do calculation. I don't care. Okay. This one also. Now, the last one. Common gate. You understand when they get the amplifier, like a bipolar common admitter, then you must understand that in AC admitter will be round. Common collector in AC collector will be round. Common base in AC the base will be round. Same thing apply for the JFET. When they say common drain, guarantee in AC drain will be round. Common source in AC source round. Common gate, that will be telling you gate will be rounded. Normally you understand a little more in the bipolar, so that will be not a problem. They almost the same. Common gate, input applied to the source and output from the drain. And also telling you that will be G in and that will be G out. And that AC equivalent. Okay. And G in will be equal RS parallel 1 over GM. G out, in this case, you get RD only. Make sure if you get the load, that means the load have to parallel with RD. And the gain will be GM times RD. What they said, common gate amplifier configuration had no phase shift between input and output by in phase. Okay, go ahead and do this calculation for me. If we get it done, then you can go home.
Yeah, you can go from the living room to the kitchen, right?
But Mr. Smith must get much better to me. Sometimes you're confusing with the formula.
Right. Okay, and
We already did on the other one. I believe on this one should be no problem. I just want to get the answer that will be happening for students. They get lost. It's a very good document from a university, but they still confusing for VP and VG at all. When you're working with the and channel, then VG at off will be negative. And therefore, handout here will be must be reviewed to correct whatever we see they did wrong.
yeah.
Five millisiemens.
GM0 equal 5.
5 millisiemens.
Okay, 5 I'm at. GM
2.25.
2.25.
Millisiemens.
G in the formula R at parallel 1 over GM. Okay, who get the input impedance?
I calculated 317 ohms.
First thing you need to calculate the GM 1 over GM. 1 divide 2.25 equal and I plot 1.1 equal. Revert that. Okay. .44. Okay. Okay. So 1.1 times 0.44 divide 1 plot 0.44.
One 1.1 plus 0.44.
So what you get? For my calculation, I get 0.34.
I think your value of GM0 and GM is incorrect.
Okay. So GM 0.
So if you take the, oh, hold on, that's, hold on, that's 20, yeah, that's correct, sorry. I was looking at a different number.
So I get 314 ohms.
Exactly. 0.344.
Yeah.
31.
Four.
0.31.
GLEG. Equal RD 3.6K. Okay, the last one, AV and VL. GM times RD. GM 2.25. RD 1.1K. That means make sure you got to get a right unit. .25 times 10 minus 3 times 1.1 times 10 power of 3 that will be given you 2.25 times 1.1.
Mr. Pham, RD, shouldn't RD be 3.6?
RV. AV, is it you get 2.25 times 10 minus 3
Times 3.6.
times 1.1, right?
No, 1.1 is the source, isn't it?
Oh, okay, let's see. Right now, AV time RD, sorry. Okay, you're right. Okay, let's see. GM, okay, time RD. RD will be 3.6K
Correct.
times 10 power of 3. Okay, so basically you get 2.25 times 3.6,
8.1.
8.1. Okay, V out.
Hey, while you're doing that, can somebody tell me what you got for ZN?
You mean on number B, right?
What ZN?
It's as
C.
Mr. Pham has it, 0.34K.
Right here.
Okay. I've been hitting the wrong buttons. After we finish this class, I'm going to go over this again anyway.
Okay, that's it.
Looks good.
I hope for every student, if I already given you on up the formula, you're able to do your calculation. You don't have to memorize any formula. Okay. But you already get everything and you still cannot calculation. That's a problem. Minimum requirement for the technician. Hello, Sam.
Hello, Mr. Pham.
Yeah, after tomorrow, I need to send to me the status of the tech one,
Yes, sir.
so I can evaluate to see who can be registered for tech two.
Okay. Yes, sir. By tomorrow. Okay.
After the test tomorrow.
Okay. After test. Okay. After test tomorrow. Okay.
Okay, any question?
I have a question, but it's concerning the final exam for Tech 1. Will it be in class or will it be like online? Will we have to download it and then, take it like we were taking the quiz on our computers?
Okay, now. Final, the same like the quiz,
So it's online.
right? Same
Okay.
like the quiz, we not upload anything. Only thing the difference will be the quiz, you get 18 questions. Final, you get 50,
Okay.
okay?
And then I have one more question concerning the final exam.
Mhm.
Is there a possibility like we can look over to see what we got wrong? That way, you know, we can in the event if we were to happen like say wanting to retake it, we could study it and then retake it and then get a better score.
Okay, let meeting over. And we'll let you guys know
Okay.
next week.
Okay then. Thank you.
I think I don't want to fail anyone.
Nobody wants to fail.
Yeah, that's what I want also. Okay, to spend much time, some different level, so some very good. However, you know, why different? I want to help you guys. Okay, and when you get the complete certification, you apply for the job basically depending on yourself. But the best I can do, try to help you get the chance. Okay, so don't worry about anything. Final test, look over quiz number 1 to quiz number 10 tomorrow. If you go through that, you know how to do what to do. At least you can get a C to pass the course. Otherwise, I have to let you make it up.
Thank you.
Welcome. I don't want to spend too much time and finally you cannot get through it. Not like the college. The college, they don't care. But the college, they cannot compare to this program. They just doing much theory for too many years. That's for AS degree, like the technician. But after the complete that AS degree, they still cannot doing technician job. We're doing quite different. That's what the professor in the AS degree, they asking me to send them sample. What we doing, what the digital lab we doing, quite different what they do. They want to do like we do it. They cannot, they don't have a budget to buy the level, too much money. So everything they doing up there by manual, not like we doing like the company do it. Okay, so that's it. You get any question?
Mr. Pham, you're gonna put the thing on the recording tonight, correct?
Exactly.
Okay, thank you.
Okay, if it's not, then good night, everyone.
Good night, Mr. Pham.
Good
Mr.
night.
Pham,
Good night.
Aye.
Take care, everyone.
Mr. Pham, I have a question for you.
Okay, go ahead.
The P-Spice simulations that were added last week were a little tricky for the filters. Is there a good video that you've done in the past, or does somebody have a video out there of how to run the simulation? I've got everything set up. I'm not sure how to do the AC pass on it to get the output.
Bring it to the lab, we'll go over it.
Okay.
Maybe he could share screen and we could do it real quick.
We'll go over it in the lab. It's probably more complicated. There's obviously a lot to see. It would just be nice to be able to see. I watched a few videos. I just can't quite grasp how to get the output that's required for the Excel spreadsheet.
What the homework?
Pardon me?
What is the assignment number?
There's 3 of them, I believe, 21, 22, and 23.
Okay,
I set up 21. The other 2 I haven't started because I couldn't figure out how to do the output on 21.
okay. I see.
So we'll go over it on Wednesday lab time.
Okay, so let's see. You know how to run the pitch file, right?
I know how to set it up. I don't know how to run
Oh, okay.
the output.
Okay. So, Sam, you think
Yes,
you
sir.
can have it tomorrow?
Yeah, I can. Yeah, I can do a quick simulation here if you want to see.
The
Okay.
AC sweep is what I wasn't sure about. There's, I'm assuming you guys have a start frequency of 30 and you go up to 10K, but it wasn't giving me an output that made sense relative to what you have to put into
Okay.
Excel. So
Okay,
Okay,
let's
so-
check on it and I can tell you.
Okay, so let me see assignment. Which assignment do you want me to look over?
21 would be helpful.
21.
21. Okay. Okay, so I'm going 21, maximize it. Okay, so I'm gonna file open assignment 21, band pass filter. Okay, something, let me see, enlarge it. This is the one, right?
That's it, correct.
Okay, so you set it up and then according to the Excel, you want to look at the, so once you have this schematic set up, you want to do just go up to analysis and you want to click on setup. Okay, and you want to click on this, say AC sweep.
Gotcha.
And then you want an AC sweep, we want a decade line. Okay, so we want to choose the decade. And then the end frequency, according to this, according to the Excel, it's set at 10K. So you set at 10K there, and you want to click OK. That's the parameter you need. Okay.
Perfect. I got that far.
Okay, and then once you have that, and then you click, and once you have save it, and then you want to do it, go to analysis and then click on simulate or F11 to run the simulation. Okay, so you want to click on that and then it should be simulating. Let me see, it's collecting the data. Okay, so here it is. So you should get in like a black screen like this.
Got that.
Okay, and then once that, now you can use the graphical information right on top here, or you can go up on the menu here. It's called trace. You want add trace, and then you want to do a filter out everything. We need it just the V out for this case because that's all you need to collect the data for. Okay, so we need to collect on data V out, so therefore we need to filter everything. Now we have V out. Okay, so you click on that, and that trace expression show down here. Click OK, and now display here on the graph.
Okay, I got that.
Okay. And then after that, you want to do is, like I said, you can use the graphical methods here, or you can use the menu on top. So I go trace, and I look at the cursor, and I want to put a display. Now mine can sort of display it differently. I'm missing something, so it doesn't show on mine. But you see this line here. So you can use your arrow on your keyboard to move the cursor to location where you need to look at. So the first one look like at 30 Hertz. So you want to do just put right over here at 30 Hertz. Okay. Now mine's sort of different, so I can't, let me see. So that right there, it's showing that at close to 30 hertz, it's at 84.724 millivolt.
Hey, Sam,
So
if I could jump in and just ask, where's that box at when you clicked on?
Like I said, this box, it looked like my computer is not showing what the box, so you have to, now yours would show you what the box, so it would show A and B, show the x-axis and the y-axis. Now mine doesn't look like something is going on with my computer, so let me see. So normally you have is so once you've done simulation, you should be coming. So you have your simulation like this, and so you have something right here that's showing that at that point it's showing A1. So A1, it should be pretty close to that 30 hertz, and this is the voltage that showing up.
So the gain, the decimal, and the voltage out. Okay.
Yeah, so you got this one is this is the first one represent the frequency. The second one represent the voltage of the y-axis.
Okay. So at 30 hertz, the voltage out, 84.8.
Right.
The
Millivolt.
gain.
And then you want to do is convert it to volt, make sure, because they want the answer in volt.
Okay. All right. So, okay. All right. So we put 3 volts in, we calculate the gain, and then we'll calculate in decibels. Okay.
Correct. And then you will look at and then you calculate the V out. So therefore you take whatever you got there, divided by what you put in. In this case, for this circuit is 3 volt. So divided by 3, that would give you your gain value.
Okay.
And then you do the calculation for the decibel.
Gotcha. All right. And then at the bottom, V out at F center.
Yeah, so
lower
you want to
cutoff.
do, so you
same
just have to
thing.
do it just on this one, you can do in schematic. And let me see if you can click on the ones that the maximize here. So take me directly here to where the center frequency is at.
Okay.
No, I don't have, so there it is. Center frequency is 329.610 kilohertz. Hertz
Mhm.
at 3.1907. See, as it's way beyond what we put in, which is 3 volt. Okay.
Okay.
So that's
Makes
at the
sense.
maximum. Yes.
Okay.
So that you look at the frequency, and then after that you take whatever the maximum here times that 0.707. That would tell you where you're going to be at your cutoff frequency, which is this one, about 2.26. So somewhere over here, 2.26. So somewhere in between here. So somewhere right here would be somewhere would be the cutoff of the first one. Would be somewhere here. Yeah. So. Oops, let me think. Yeah, so that's how you do it. Just kind of use your mouse and then after that use your keyboard with the arrow moving left and right, and so you can move into the location. Now you can also use this one. You can also zoom into the location. You can use a zoom here. You can call zoom in the location where you want to look at that. Now you look at very, very clearly. Okay.
Gotcha.
And then you can click on this one to go back to normal. Okay, so back to normal circuit.
Okay, I got all the same output. I just didn't go far enough. I wasn't sure how I was going to get the gain and the decibel, but I guess I could have just followed the formula. But no.
Okay, yeah, just work on it. And if you have any other question, you bring it up tomorrow and we can definitely help you. Okay.
Great. Thank you very much. I appreciate it.
You're welcome. Okay.
Okay, cool.
Thank you, Mr.
Have
Pham.
a good night.
You have a good
Thank
night.
you, Sam.
You're welcome.